Hello friends, in this lecture we'll discuss some applications of Taylor's theorem and Lorentz theorem. That is, some examples based on Taylor's theorem and Lorentz theorem. First of all, we will see what is meant by Taylor's theorem. Here, this is regarding Taylor's theorem. If f is analytic in a domain D, then for Z with center A, radius R in the domain D, f has the Taylor series expansion f of z equal to summation for all n greater than or equal to 0 an z minus a to the power n, where an is nth derivative of f at a divided by n factorial, or it is also given by 1 upon 2 pi I integral over c f of xi upon z minus a to the power n plus 1. This is the Taylor's theorem, where this curve is in the domain and curve is a circle having center A, radius small r, where small r is less than capital R there. Now what we are saying here, it is a disk. So if we have such a domain D, if a function is analytic in this domain, then for any z lies in this disk having center at A and radius capital R. Z is lies here, anything, somewhere here, Z is anywhere here. And what about C? C is the circle, again inside this disk. This is your C, curve C. Inside C, whose radius is small r, which is strictly less than capital R, and then in this case f of z is nothing but summation over all n greater than or equal to 0 an z minus a to the power n, where n is given by either this or this, Now what is the use of this one? It's a first use is before we solve these two examples, we'll find the Taylor series expansion about e to the power z. First of all, about 0. E to the power z about 0. What will happen? E to the power z, let f of z is equal to e to the power z. Therefore, f dash z is equal to what? Again e to the power z. We know that f double dash z is what? Again e to the power z. In this so on, f nth derivative of z is e to the power z. This implies f of 0 equal to e to the power 0 equal to 1, right? F dash at 0 equal to again e to the power 0 equal to 1, up to so on. F nth derivative of 0 at 0 equal to, it is equal to 1 again. So f nth at 0 of f of z is equal to 1, and therefore Taylor series expansion, this f of z, is nothing but summation n greater than or equal to 0 an z minus 0 means z raised to n, where an is what? F n at 0 upon n factorial. F n at 0 is 1 upon n factorial. So therefore this becomes summation n greater than or equal to 0. What is an? 1 upon n factorial z raised to n. That is summation for all n greater than or equal to 0 z raised to n upon n factorial. And so this will give, by putting n equal to 0, we get first 1 plus n equal to 1 z plus z square upon 2 factorial plus z cube upon 3 factorial, and so on and so on. This is your f of z. So we know that e to the power x is also like this, and so e to the power z is that. Similarly, you can also find sin z. If g of z equal to sin z, you can obtain the Taylor series expansion regarding sin z. So G dash of Z is equal to what? Cos Z. Cos Z can I write? Sin pi by 2 plus Z. Sin pi by 2 cos Z plus cos pi by 2 sin Z. This then G double dash at Z is equal to. Its derivative is cos of pi by 2 plus Z. That can be written as sin of pi by 2 plus Z plus pi by 2 means 2 pi by 2 plus Z. And therefore, nth derivative of G of Z is nothing but sin n pi by 2 plus Z. So, if we want to obtain the expansion Taylor series expansion of sin Z about Z equal to 0, then therefore an becomes, what about an? Fn at 0 upon n factorial. What is fn at 0? Sin n pi by 2 divided by n factorial. What about sin n pi by 2? We know that sin pi by 2 is what? 1. Sin 2 pi by 2 is 0. Then sin 3 pi by 2 minus 1. Sin 4 pi by 2, 0. So sin n pi by 2 is 0 if n equal to 0, right? Then n equal to 2, n equal to 4, 6. All even angles are 0. Then it is either plus 1 or minus 1 depending on this n is. If n is equal to 1, then it is plus 1. N equal to 5 plus 1. N equal to 9 plus 1. And for this, n equal to 3, 3 pi by 2 minus 1. Then 7, for 7 it is minus 1. Then for 11 it is minus 1 and so on. And therefore, your G of Z, that is sin Z, is equal to summation n greater than or equal to 0 sin n pi by 2 upon n factorial into Z raised to n into Z raised to n. Now, so for n equal to 0, sin 0 is 0. So first term becomes 0. Plus for n equal to 1, it is 1 upon 1 factorial into Z raised to n means Z. Plus for n equal to 2, it is 0. For n equal to 3, it is minus 1 upon 3 factorial Z cube plus 0 plus 1 upon 5 factorial Z raised to 5 and so on. So your expansion is Z minus Z cube by 3 factorial plus Z raised to 5 by 5 factorial, then minus Z raised to 7 upon 7 factorial plus Z raised to 9 upon 9 factorial and so on, which is same as complex real sin x. This is the expansion. What is the expansion of sin x? X minus x cube by 3 factorial plus x raised to 5 by 5 factorial minus x raised to 7 by 7 factorial and so on. In the same way, if your h of z is cos z, then its expansion is 1 plus z square upon 2 factorial plus z cube upon, sorry, z raised to here 1 minus z square upon 2 factorial plus z raised to 4 upon 4 factorial minus z raised to 6 upon 6 factorial and so on. You go with this. So you go with this cos z. In this case also, if you have h of z is this one, then nth derivative of z, h of z is cos n pi by 2 plus z. It is again that n pi by 2 plus z. And again, if I put z equal to 0, this we get cos n pi by 2. Again, cos n pi by 2 is either 0 or plus 1 or minus 1 depending on values of n, and that will give us this one. Okay. So by using this Taylor's expansion, you can find the expansion of sin z, cos z, as well as e to the power z. Now we will go for this example. What about here? Z minus 1 upon z square minus z minus 1. Z minus 1 upon z square minus z minus 1. F of z equal to z minus 1 upon z square minus z minus 1, which is equal to, what about z square minus 1 minus 1? Z square minus 1 minus 1. 1 minute. We'll go for that example. It should be 2, not 1. Z square minus z minus 1. Z square minus z, not minus 1, but it should be minus 2. How you can write it? It is equal to z minus 1 upon z square minus 2z plus z minus 2. Means factors 2 in such a way that their subtraction becomes minus 1. So 2 ones are 2, minus 2 plus 2. This can be written as z minus 1 upon z into z minus 2 plus 1 into z minus 2, which is equal to z minus 1 upon z minus 2 into z plus 1. That can be written as a upon z minus 2 plus b upon z plus 1. You have to find Taylor series expansion about z equal to 0. About z equal to 0. This is nothing but a into z plus 1 plus b into z minus 2 divided by z minus 2 into z plus 1. We know this. This is equal to, so this implies this and this one both are same. So this implies z minus 1 equal to a into z plus 1 plus b into z minus 2. We want to obtain the values of a and b now here. Put a equal to 2, sorry, z equal to 2 in this expansion. We get, if I put z equal to 2, we get 1 equal to 3a, that is a equal to 1 by 3. And if I put z equal to minus 1, this becomes 0. For z equal to minus 1, it becomes minus 2 equal to b into minus 3. That is b equal to 2 by 3. And therefore, your f of z, which is z minus 1 upon z square minus z minus 2, is nothing but 1 by 3 upon z minus 2 plus 2 by 3 upon z plus 1. Now we know that at z equal to 0, this whole function is analytic. At z equal to 0, this whole function is analytic. So we can find the Taylor series expansion about z equal to 0 of this function. We can find Taylor series expansion about z equal to 0 of this function. Okay, I will call this as f1z plus f2z. Okay, f1z plus f2z. We'll find one by one now. The Taylor series expansion of f1z about z equal to 0 and that of f2z again about z equal to 0. About z equal to 0, about z. Now, for f1z, what is f dash of z? F dash of z equal to 1 by 3 into, actually it is derivative of what? Z minus 2 to the power 1. So we get minus 1 into z minus 2 to the power minus 2. This is the first derivative. What about second derivative? 1 by 3 minus 1 minus 2 z minus 2 to the power minus 3 and so on. What is the nth derivative of z? It is, this is 1 by 3 into minus 1 minus 2 up to minus n, up to where? Minus n into z minus 2 to the power minus of n plus 1, right? Minus of n plus 1, which is equal to, can I write this as 1 by 3 minus 1 to the power n upon z minus 2 to the power n plus 1, and there it is n factorial again, minus 1 to the power n into n factorial. This is fn at z minus 1 to the power n factorial upon z minus 2 to the power n plus 1, and therefore I will call this as a1n, isn't it? a1 of n means what? Coefficient here, a1n equal to, what you will get? f1n at 0 upon n factorial. So this is equal to f1n at 0 is what? By putting z equal to 0. What about this? If I put z equal to 0 here, we get 1 by 3 minus 1 raised to n into n factorial upon z equal to 0 minus 2 to the power n plus 1, and this is into n factorial. So this becomes only 1 by 3 minus 1 to the power n divided by minus 2 to the power n plus 1. Minus 1 to the power n divided by minus 2 to the power n plus 1, which is equal to 1 by 3 minus 1 raised to n upon minus 2 to the power n into minus 2. So can I write it as minus 1 upon 2 into 3, 6 into minus 1 to the power n upon minus 2 to the power n. You can write this as 1 by 2 to the power n. Minus 1 by 6 into 1 by 2 to the power n. This is what? a1n. And therefore, f1z can be written as summation n greater than or equal to 0, isn't it? an is what? Minus 1 upon 6, 1 by 2 to the power n into z to the power n. This I will call equation number 1. This is for what? f1 of z. This is for what? fn of f1 of z. Now, for f2 of z, right? What about f dash z equal to? What is f2 of z? f2 of z is what? 1 upon, this is f2 of z, 2 by 3 upon z plus 1. What is it? So 2 by 3 upon z plus 1. So f2 of z is nothing but 2 by 3 into 1 upon z plus 1. That is 2 by 3 into z plus 1 to the power minus 1. So what is f2 dash at z? It is equal to 2 by 3 minus 1 z plus 1 to the power minus 2. f2 double dash at z, this 2 by 3 as it is, minus 1 minus 2 z plus 1 to the power minus 3, and so on. Therefore, f2n at z becomes, what is f2n at z? This 2 by 3 as it is. If I take second derivative, minus 1 minus 2. So nth derivative, minus 1 minus 2 up to where? Minus n into z plus 1 to the power minus of n plus 1, increased by 1, minus n minus 1, isn't it? So this is equal to 2 by 3 minus 1 raised to n, we have taken minus 1 from each of these, into n factorial divided by z plus 1 to the power n plus 1. Okay, so what is f2n at 0? This becomes 2 by 3 minus 1 raised to n into n factorial. If I put z equal to 0, we get 1 to the power n plus 1, we get 1 only. So this becomes 2 by 3 minus 1 raised to n into n factorial. And therefore, now I will take a to n as the coefficient, f2n at 0 upon n factorial, which is equal to this 2 by 3 minus 1 raised to n factorial upon n factorial. We get only 2 by 3 into minus 1 to the power n into minus 1 to the power n. And hence, therefore, your f2 of z becomes a to n 2 by 3 summation for n greater than or equal to 0 2 by 3 minus 1 raised to n z raised to n. I will call this as 2. What about 1? 1 is what? This one, summation over n greater than or equal to 0 minus 1 by 6 1 by 2 to the power n into z raised to n. And therefore we have to add f1 plus f2. And therefore f1 plus f2 is, therefore f of z, which is nothing but f1 at z plus f2 at z, which is equal to, what is f2 at z? Summation n greater than or equal to 0 2 by 3 minus 1 raised to n z raised to n plus, what is f1z? Summation n greater than or equal to 0 1 minus 1 by 6 1 by 2 to the power n minus 1 by 6 plus 1 by 2 to the power n into z raised to n. And so can I write this as, this is nothing but summation n greater than or equal to 0 in first bracket minus 1 by 6 into 1 by 2 to the power n plus 2 by 3 into minus 1 to the power n into z to the power n. This is the f of z. That is the Taylor series expansion of fz. What is fz here? Fz is z minus 1 upon z square minus z minus 2. Okay, so for this power series, an is this one now. An is this one. Okay, an is this one. Right now, so this is required Taylor series expansion. Taylor series expansion about z equal to 0. In this way, we can form the Taylor series expansion. You have one more example here. And which is that? 1 upon 1 minus z plus z square. 1 upon 1 minus z plus z square. Okay, so second is, let z equal to 1 upon 1 minus z plus z square. We can write it as minus 1 upon z square plus z minus 1. Z square plus z minus 1. But it is not in perfect root method. Okay, so I will write it as 1 upon z square plus z plus 1 by 4 minus 1 by 4 minus 1. How we are writing this as? Making perfect square. 1 by 2 coefficient of z, it's a square. 1 by 2, 1, it's a square. Why we are writing like this? That can be written as minus 1 divided by, what about this? This is your z plus 1 by 2 whole square. Z plus 1 by 2 whole square minus 5 by 4. How we can write it as again? It is equal to minus 1 upon, this is our z plus 1 by 2 whole square minus square root of 5 by 2 whole square. This is in the form of a square minus b square. What is it now again? Minus 1 divided by, this is your z plus 1 by 2 minus root 5 by 2 in one bracket and z plus 1 by 2 plus root 5 by 2 in another bracket. Okay, which is equal to minus 1 upon, what about this? Minus 1 upon, this becomes z plus 1 minus root 5 upon 2, and here here, what you will get there now? Z plus 1 plus root 5 upon 2. Z plus 1 plus root 5 upon 2. Okay, these are the two. Z plus 1 minus root 5 upon 2 into Z plus 1 plus root 5 upon 2. I will write it as A upon Z plus 1 minus root 5 upon 2 plus B upon Z plus 1 plus root 5 upon 2. Is it like this? A minus B. This is A square. 1 minute. 1 minus Z plus Z square. That can be written as Z square plus Z. Z square plus Z minus 1. We'll take what is exactly that example. 1 minus Z plus Z square. No. The example is what? 1 minus Z plus Z square. 1 minus Z plus Z square. Correct. So if I take minus 1 common. No need to now take common here. Actually, this becomes okay. So no need to write this. 1 minus Z plus Z square. So it is only Z square minus Z plus 1 is there. Sorry. 1. We will remove this one. We'll remove this one. Yes. Okay. So this is 1 upon Z square minus Z plus 1. Correct. Now we'll make it as perfect square. 1 upon Z square minus Z plus 1 by 4. Right. Minus 1 by 4 plus 1. Minus 1 by 4 plus 1. This is equal to 1 upon. This is nothing but now Z minus 1 by 2 whole square. And what about here? Z minus 1 by 2 whole square. So minus 1 plus 4. That is minus 3 upon 4. What is it? It is equal to 1 upon. This is Z minus 1 by 2 whole square minus square root of 3 upon 2 square. And now this becomes 1 upon Z minus 1 by 2 minus root 3 by 2 into second bracket Z minus 1 by 2 plus root 3 by 2, which is equal to 1 upon Z minus 1 by 2 minus root 3 by 2 means Z minus 1 plus root 3 upon 2 into second bracket Z minus 1 minus root 3 upon 2. 1 minus root 3 upon 2. It is like this. And now we want to write this as, which is equal to A upon, you want to write in this way, A upon Z minus 1 plus root 3 upon 2 in first bracket plus B upon Z minus 1 minus root 3 upon 2 in the second bracket. So this implies, what is the numerator here? 1 is equal to A into Z minus 1 minus root 3 upon 2 plus B into Z minus 1 plus root 3 upon 2. So to obtain the values of A and B, first of all put Z equal to 1 plus root 3 by 2 here. If I put Z equal to 1 plus root 3 by 2, this will be vanished and you will get 1 equal to A into bracket 1 plus root 3 upon 2 minus 1 minus root 3 upon 2. This gives us 1 plus root 3 minus 1 minus 1 minus minus plus root 3. So we get 2 root 3 upon 2, a into 2 root 3 upon 2, which is equal to a into root 3 only. And therefore, a is equal to 1 upon root 3. Similarly, to obtain the value of b, we will put z equal to 1 minus root 3 upon 2, so that we will obtain this coefficient of a becomes 0, and for this, so it implies 1 equal to b into 1 minus root 3 upon 2 minus 1 plus root 3 upon 2, which is equal to, this implies 1 equal to 1 minus root 3 minus 1 minus root 3. So we get minus 2 root 3 upon 2, that is only minus root 3. And so b is equal to, this implies b equal to minus 1 upon square root of 3. Minus 1 upon square root of 3 you will get. And hence, your now f of z becomes a upon, means 1 upon root 3 divided by z minus, what you will get there? 1 plus root 3 upon 2. 1 plus root 3 upon 2 minus 1 by root 3 divided by z minus 1 minus root 3 upon 2. 1 minus root 3 upon 2. Okay, that will be the case. Hence, now see here. Now, this is f1z plus f2z. f1z plus f2z. Now, to obtain the Taylor series expansion about z equal to 0 of f1z, we need to find f1 nth derivative at z. f1 nth derivative at z. Now, we know that this 1 by root 3 is constant, and this is of the form z minus a. And we know that the derivative of z minus a, 1 upon z minus a, that is z minus a to the power minus 1 is again, as in the previous, minus 1 to the power n into n factorial divided by z minus 1 plus root 3 by 2 to the power n plus 1. So its nth derivative becomes 1 by root 3 minus 1 raised to n into n factorial upon z minus 1 plus root 3 upon 2 to the power n. Therefore, its coefficients a1n becomes f1, so this implies f1 nth at 0 equal to 1 upon root 3 minus 1 raised to n into n factorial divided by, we have to take minus of 1 plus root 3 upon 2 to the power n by putting z equal to 0. Therefore, a1n is divided by n factorial. So n factorial cancels with n factorial. We get 1 upon root 3 minus 1 raised to n upon, what about here? Here is minus 1 raised to n into, I will take minus 1 common, 1 plus root 3 by 2 to the power n. You will get that like this. So this is nothing but 1 by root 3 into 1 upon 1 plus root 3 divided by 2 to the power n. This will be a1n, and therefore f1z becomes summation for all n greater than or equal to 0, 1 by root 3 into 1 upon 1 plus root 3 by 2 to the power n into z raised to n. Similarly, for f2z, what is f2z equal to? f2z is minus 1 by 3 z minus 1 minus root 3 by 2 minus 1 upon root 3, right? 1 upon z minus 1 minus root 3 by 2, right? This is 2 not z. This implies f2 nth of z equal to this minus 1 as it is into minus 1 raised to n factorial. This one root 3 is also as it is, z minus 1 minus root 3 by 2 to the power n plus 1. And so f2 nth derivative at 0 becomes f2 nth derivative at 0 becomes this minus 1 upon root 3 into n factorial cancels with n factorial. Sorry, it is not n factorial. I have to put only z equal to 0. So we get minus 1 raised to n factorial divided by minus 1 minus root 3 by 2 to the power n. That can be written as minus 1 upon root 3. Now here minus 1 raised to n I will take outside, and you will get minus 1 raised to n cancels with minus n raised to n, minus 1 n factorial divided by 1 minus root 3 upon 2 to the power n. And therefore coefficients in second Taylor series expansion, this is upon n factorial. So n factorial minus 1 upon square root of 3 into 1 upon 1 minus root 3 whole divided by 2 to the power n. And therefore f2 of z becomes summation over all n greater than or equal to 0 minus 1 upon root 3 into 1 upon 1 minus root 3 upon 2 to the power n into z raised to n. So this is for f2 of z, and this is for f1 of z, isn't it? This is for f1 of z, and therefore f1 plus f2 is your f of z, and therefore f of z is nothing but f1z plus f2z, means this summation n greater than or equal to 0 minus 1 upon root 3 1 upon 1 minus root 3 upon 2 to the power n into z raised to n. And what about here? Summation n greater than or equal to 0 1 upon root 3 1 upon 1 plus root 3 by 2 to the power n, right, into z raised to n. This is f1z, right, f1z. And thus as 1 by root 3 is common, so 1 by root 3 summation n greater than or equal to 0 1 upon 1 plus root 3 by 2 to the power n minus 1 upon 1 minus root 3 by 2 to the power n in bracket into z raised to n, into z raised to n you will get here. Okay, you can again simplify this by taking product of these two and cross multiplication, but this is also sufficient. F of z. So this is the Taylor series expansion of f of z about z equal to 0. About z equal to 0. This, how you can write it as? This can be written as 1 by root 3 summation n greater than or equal to 0. This is 1 minus root 3 by 2 to the power n minus 1 plus root 3 by 2 to the power n divided by product of these two. 1 plus root 3 by 2 to the power n into 1 minus root 3 by 2 to the power n into z raised to n. That can also be written as 1 by root 3 into summation for n greater than or equal to 0. This will keep as it is. 1 minus root 3 by 2 to the power n minus 1 plus root 3 by 2 to the power n divided by both to the power n. A into b to the power n means what? A to the power n, b to the power n. So we get 1 by 1 plus root 3 by 2 into 1 minus root 3 by 2. 2 you will get 4. 1 plus root 3 into 1 minus root 3. That is 1 square minus root 3 square. So 1 minus 3. 1 minus 3 is minus 2. Minus 2 by 4. Minus 2 by 4 means 1 minus 1 by 2. So you will get minus 1 by 2 to the power n into z to the power n also. So this can be done. This can be done. Okay. So this is also the power series, Taylor series expansion of that f of z. What f of z we have taken? F of z was this one. One upon 1 minus z plus z square. So in this way, we can find the Taylor series expansion about z equal to any point. Now here about z equal to 1 you can find, z equal to 2 you can find, z equal to 3 you can find. But Taylor series is about that point at which the function is analytic. At which the function is analytic. And this condition may not be in a Laurent series. Some examples on Laurent series we will discuss in next lecture. Okay. So for this, we have made these things. Okay. We'll stop here.